Hi, and welcome to our next video looking at predicting the formation of a precipitate. So in our last lesson we looked at the solubility product and how that was calculated, and we did quite a few different examples in a few different formats of how we could actually calculate the solubility product. So today we're going to take that information and take it to the next level and working out, well, how can we predict whether a precipitate will actually form or not? So this is a really handy slide which outlines all those conditions of whether a precipitate will occur or not. So if we have a look here, if we have two solutions that are combined and we write our reaction out, how are we going to know if a precipitate has actually occurred or not? So earlier in this module we had calculated the KEQ for a reaction, and that was the equilibrium constant for a reaction that was actually at equilibrium. And then we also have the reaction quotient, which is for the calculations where it hadn't yet reached equilibrium. Well, we have the same thing working here. In this case now it's called the ionic product. So we have our solubility product when it has reached equilibrium, and now that we have our ionic product, which is when we have the same sort of equation, but it may not have reached that point yet. So if we have a look here, the calculations, like before, are the same. Now, if we look at this example here, we've got aluminium chloride, and again, we've got our QS is the concentration of the silver ions and the chlorine ions. And now, whereas before we compared our KEQ to the Q value, here we are comparing our QS to our KSP, and to see whether a precipitate might have occurred. So if we've got the QS, so the ionic product is less than the solubility product, the solution's not saturated. If we've got them equal, it's saturated and therefore at equilibrium as well. And if it is greater than the KSP, it's supersaturated, and then we know that a precipitate will have formed. So let's have a look at an example. So if I've got 0.500 grams of barium hydroxide placed into 200 mils of water, it's stirred, we need to determine whether a precipitate will form. Now we've got our KSP here for barium hydroxide, which is 2.55 times 10 to the minus 4. And the first thing we do is we write our equation. So we've got barium hydroxide precipitate is forming barium ions and hydroxide ions in water. Now, the first thing we need to do is work out, well, how many moles of barium hydroxide have I got? So I've got 0.5 grams over my molar mass of barium hydroxide, which is 171.3 grams. So when I work that out, I find that I have got 0.029 and so on moles of barium hydroxide. So now I go to my next equation. Concentration is equal to moles over volume. So we've got our number of moles. You'll notice I've kept all the numbers there so that we can round at the end, divided by 0.2. And I get 0.0146 moles per litre. Now, as before in our last lesson, there are other ways we can do this. Some of us might prefer to divide, first of all, by 0.2, which is converting it from grams per 100 mils to grams per litre, and then doing the calculation with the moles. Whichever way you choose to do it is totally fine. Just make sure you stick to the one way so that you're not confusing yourself. So we've got the concentration there of our barium hydroxide. So before we go, we need to notice here that we've got a 1:2 ratio here. So that needs to be taken into consideration. Let's go to the next section. So here I have got my barium ions are in the same molar ratio as my barium hydroxide. So because they are in the same ratio, it is the same concentration there. But you'll notice there the hydroxide ions, it's 2 lots of that concentration. Again, due to that molar ratio that we said just over here before. There are 2 lots of that, so we need to have 2 lots of it in the next slide. So now we do our QSP. That's our ionic product, and working out our concentrations at this point in the reaction. So I have got 0.0146 as our concentration of barium ions, and 2 lots of that, which is 0.0292, and again, because of the number in front, or the coefficient in front of the hydroxide, means to the power of 2. So we get an answer of 1.24 times 10 to the minus 5, and in this case, that QSP is less than the KSP that was given on the previous slide, and therefore no precipitate occurred. Now here are some examples that you can try. So my suggestion is pause the video, go through and do those answers and see how you go, and then we will come back and I will give you those answers and put them on OneNote so that you can compare them then. So something else we need to look at when we are looking at predicting whether a precipitate will form, and that's something called the common ion effect. So most of the reactions that we've done so far is just looking at one salt in solution, but what happens when there's another salt dissolved in solution? What happens then to the solubility? So let's have an example to help us explain this. So we've got some sodium sulfate that is added to a solution that has already got calcium sulfate in it. So we need to channel Le Chatelier again and use that principle to help us decide what's going to happen. So we've got calcium sulfate in our test tube, and it's a precipitate or a solid, it's insoluble, and it will form the ions of calcium 2 plus and sulfate 2 minus, both are aqueous forms. Now the sodium sulfate's a soluble salt, so it will dissociate. When we put it into that solution, it will dissociate into its ions in that solution. So we have now got sodium ions and sulfate ions. Now you can see there that sulfate ions are common both to the calcium sulfate and also the sodium sulfate. So we are actually now getting an increase in those sulfate ions. So when I increase those sulfate ions, it's going to favour the reverse reaction. Now in doing so, it's going to decrease, or we're going to use up some of those calcium ions, and we are going to make more of the calcium sulfate as it moves in that reverse direction. And in doing so, it will increase the mass of that. So now it's going to even be more insoluble than it was to start with. Now, there's another way that we can do this with looking at our ice tables. These are really, really handy to use when we're talking about what we've got in the beginning and what we have at equilibrium and what changes happen. And it's a really clear way so that you can make sure that you're not missing anything out. So in this example, lead 2 chloride has a KSP of 1.7 times 10 to the minus 5 at 25 degrees Celsius. Calculate its molar solubility, so solubility per mole, in a 0.2 moles per litre solution of NaCl. So we've got some NaCl where it has been dissolved into water, and now I'm adding some lead chloride to that. So initially in that solution, I have got chloride ions, but I've got no lead ions there. Again, you need to look at your equation. Have a look at the equation there. I've got 1 lead to 2 chlorides. So what's happening is I am adding something of lead to the solution, but I'm going to be adding 2 lots of the chloride due to that mole ratio. So at equilibrium, I'm going to have S, whatever that increase was, and I had 0.2 of chlorides to start with, and now I'm adding the equivalent of 2S into that. So this is when we bring in a little bit of our algebra for those maths fans. So because the amount of chloride ions that I'm adding is fairly small, you can pretty much assume that all those chloride ions are coming from the sodium chloride solution. So mostly that 2s there is going to be fairly insignificant, and we just leave it as 0.2. So if you look down the bottom, we write our KSP. So again, it's the lead ions, the concentration of the lead ions, and then the concentration of the chloride ions. Again, it's squared due to the coefficient in front. We know our KSP, so we've got our KSP just here. We have how much the lead has changed by at equilibrium. That's how much it's going to be. And again, here is our chloride ions. So we simply substitute that in and we'll work out what S is. And here we work out the molar solubility of lead chloride in that is 4.3 times 10 to the minus 4. Now, that is lower than the solubility of lead chloride itself in water, which was 1.62 times 10 to the minus 2. And that then is our molar solubility. So using that example that we had there, have a go at these ones then as well. So pause the video, do the calculations, and I again will upload some answers for you to check. Talk to you soon.